All right, sounds good. So first of all, I'd like to thank Ashutosh and the IEEE team and Johns Hopkins for inviting me here. My name is Apurva Mody. I'm the founder and CEO of a startup company by the name of Airanaculus in the Boston area. Uh, I used to be a former vice chair and chair of National Spectrum Consortium, which is a pretty large nonprofit organization that does a lot of work in the area of spectrum. Uh, the motto of Airanaculus is intelligent RF and networking from space to smart cities. So we have quite a few contracts in this space, and then we are trying to, at some point, commercialize the company or create a commercial product. So we are moving towards that, and I'll talk about that. Starting from the basics of what bidirectional spectrum sharing is, I will, move towards the concept of network sharing and how and why we need both spectrum and network agility for next generation networks, right? So everybody knows, like, bidirectional spectrum sharing. Essentially, what it means is that you can do this based on geographies where you might have a user A, B, and C at different locations using the same spectrum, or you might have same location, but then user A and user B, they share the spectrum at different times. For example, you might have, like, 3.5 gigahertz where you're trying to share the spectrum with the radar. So the 5G and 4G and radar, they're trying to share the same spectrum. So if you look at the recent auctions, last 5 years, as well as the next auctions, everything, all bands require spectrum sharing because US is kind of unfortunate, right? United States has got, it's one of the developed countries, and so our spectrum usage is pretty dense, and everything is accounted for. And in fact, FCC created this map, uh, the very famous spectrum allocation chart, which you can find everywhere, where the allocation of spectrum was done like the real estate or farms, and every spectrum band was pretty much accounted for. And so as a result of that, our spectrum usage is pretty congested. And so if you want to use any of the spectrum for commercial usage, a lot of spectrum belongs to the federal entities as well as DoD. You will have to do spectrum sharing. So this could be like, there's a lot of discussions going on in the 3.1 to 3.55 gigahertz, where you'll need fast spectrum sharing between the radars as well as the commercial entities. And then there are like more than 30 different types of radars operating in this band, which includes AVAX as well as SPY radars, SPIN 43 and others. 3.7 to 4.2, there was a lot of controversy between the altimeters as well as the 5G. And so, this is going to keep going on, right? But pretty much all the spectrum bands have got something or the other. Even 2025 to 2110 megahertz has got NASA long links, where there's telemetry data that comes from the space, and so there's a lot of competition to access the spectrum, and we need to make sure that uh, whoever uses the spectrum does not cause interference to the other users. So let's start with a very simple example of television band white spaces. I've been in this space for a long, long time. Uh, and the whole notion was that, like, you'll create spectrum sensing and white space databases and be able to share the spectrum. So, for example, you might have this hole over here, and we call these holes to be white spaces, and then somebody can be allocated that particular spectrum. And UHF has got very good propagation characteristics. You can, like, go and use this. And my assumption is that the 6G networks, 5G and 6G, and moving forward, I mean, the 6G and other networks, uh, I mean, I'm not associating this with 3GPP, but I'm just saying that, like, the next generation networks need to be spectrum agnostic, right? They should be able to operate in all spectrum bands, because new hardware technologies are coming up that support or that allow our waveforms to be deployed in all possible spectrum bands. So the other example is this one, which is the next evolution of spectrum sharing, where you had something called as evolution from the TV whitespace database to the spectrum access system. And spectrum sensing was renamed as environmental sensing capability, or ESC. And once again, there was some notion of spectrum sharing. One of the key things here was that who is going to tell the spectrum access system that the radar is present, right? And so there was a lot of discussion around it. And so Recently, like a couple of years ago, NTIA, a few people proposed this IIC capability, which is the incumbent informing capability. So there has been a lot of push now. I mean, the discussions have already started on, like, for 3.1 to 3.45 gigahertz. In fact, I'm also the chair of the working groups within the National Spectrum Consortium, where like 200 people are participating on what the regulations should be and the use cases should be for the 3.1 to 3.45 gigahertz. And there are many different groups, like, some focusing on the band plan, some focusing on the spectrum sharing regime. But the general thrust seems to be that, like, especially the telecom operators want to go in the direction of this IIC capability. So there might be de-emphasis of the notion of, for example, a spectrum access system. And instead, what everybody wants, at least, is like some way to directly control the 5G and 6G network. So I mean, the architecture is going to shift like this. For example, that you might have an airborne radar that is coming in. You might still have an ESC, or you might have some other mechanisms by which you have incumbent informing capability. So say, for example, the government itself, it creates some sort of a messaging format, and that forms the IIC, incumbent informing capability, which is then proliferated into the network. And then the network makes or changes to the configuration. For example, if it knows that the radar is coming from a certain direction, then it will turn off uh, the power, or reduce the power in that direction, or it'll taper the beam, or it may not use a particular sector, right? So or maybe there's like a really fast spectrum sharing where the resource blocks within the 5G, they are shared with the radar. So a lot of research is happening in this area, uh, but that's where we are heading, right? So now what has happened is that it's no longer just spectrum sharing. It's actually, I mean, it's no longer spectrum optimization. It is like spectrum and network optimization, right? So we need to have both, because in order for this information to travel fast enough and proliferate across, and then the radar might be moving. This is a very difficult problem of AVAX. The radar may be moving, and so continuously this is changing, and we need to make sure that the commercial networks don't really cause interference to the radars, right? That's of paramount importance. So, this is going to be a very interesting problem as things evolve, and especially it's highly applicable to 6G networks. So another example is the 2025 to 2110 megahertz spectrum sharing from within the National Spectrum Consortium. We are just about to complete the draft specification on the recommended practice for spectrum sharing in that band. This band is interesting because this band is used by the electronic news gathering operators. So whenever the news happens, you always see this news gathering vans. They put the pole up, and there are some newscasters. So essentially, what happens is that the news is being streamed live, and then the news is transmitted from these electronic news gathering vans to the studio transmitter links, and that's where it's received. And typically they use like DVB-T standard or DVB-S2 standard. So uh, now this same spectrum band, 2025 to 2110 megahertz, is also slated to be an extension band or an overflow band for the AWS-3 spectrum. So this would mean that there are like about 38 different systems. This includes tactical data links, which are pretty high power frequency hopping systems. They can transmit at like 100 watts or so. You might have a TRR, which is the tactical radio relay, and others, and they might use the same spectrum. And then you have these really long links, which NASA uses for getting the telemetry data. So now you have to figure out like how all of these entities are going to share their spectrum. So one of the architectures that has been proposed, again, it's a different name. It's called this SMCS, or Spectrum Management and Coordination System. So this was proposed by DISA, and this has got a very similar feel to the database, right? So it's just a different name to it. And then what we proposed, Airanaculus in the National Spectrum Consortium, was to create an app, because one of the problems with TV broadcasting operators, is that TV broadcasting is a losing money losing business. Like a lot of these broadcast folks don't have a lot of funding, and they want the ease of use. So, rather than creating an elaborate mechanism, why not just create an app where, any newscaster can go in, and then, the technician can just open the app and say that, like, yeah, I'm using this particular channel. And they can provide the location, they can even provide, for example, the antenna orientation, and then it goes into the spectrum management and coordination system. And on the federal side, if there are any users, like for example, tactical data links, they can note, like, they can be notified, and they can make sure that there is no interference happening. So this is another, it's a very low cost app-based mechanism that we've proposed. So now, how do we go from spectrum agility to network agility, right? So in 5G, there's a couple of definitions on network slicing. And network slicing, as everybody knows, is creation of these virtual links. It's different from the VPN because VPN just guarantees security, but what network slicing guarantees is the quality of experience. So, what network slicing has to do is not only create an end-to-end tunnel, but it has to make sure that that tunnel provides you with the guaranteed quality of experience. And so there are three different types of network slices, right? Enhanced mobile broadband, massive machine type, and ultra reliable low latency communications. Now, is this enough, right? So, for example, if we just take this scenario to DoD operations, we don't think that this is enough. I think we need to create a little bit more designation in terms of the different slices and environments. So, everybody knows this, that like basically, network slices, they flow down the requirements of the slices down to the resource blocks, right, and resource elements. And essentially, if it's a ultra reliable low latency communication, then that particular resource block comes ahead. And if it's a EMBB, then you have like basically much higher number of resource blocks that are allocated to that particular service. So one of the challenges is like scaling the DoD operations over large geographical areas, heterogeneous, untrusted, and non-cooperative networks. Okay, so network slicing concept has been defined within a particular region, uh, where like one particular operator can manage the slices, but then operating this over large areas, where you can guarantee over heterogeneous networks, is a very difficult problem, because you have to not only control your own network and the behavior of your network, but you also have to control how your data flows across the globe. And you might have operations going on, like for example, you might have telemedicine use case or disaster response use case, or you might have electric grid recovery use case, right? So there are so many different operations, humanitarian and non-humanitarian, and you have to figure out how you can orchestrate and guarantee that quality of experience. So, what are we doing, right? So Airanaculus is working on two projects for NASA. This is for the NASA moon mission. And, both of these projects are in phase 2, SBIR. So what we did was we actually uh, organized the way network slices were created and organized. So rather than just having three categories, we said like, well, you might have higher priority for NASA, or you might have, second higher priority for the European Space Agency, right? So then you might have different missions and applications. For example, extravehicular activity. So when an astronaut is doing some sort of spacewalk, you absolutely need to have guaranteed, uh, quality of service. You have a little bit of miss in terms of heartbeats or any other kind of life support system, you're in big problem. Robotics, like descent, docking, those are the missions where you have to absolutely support. It is those missions that are critical. You might have interference from solar flares. You might have the moon-based network, which is the lunar surface network. You might have, like for example, radio astronomy applications. And say, for example, when supernova happens once in a lifetime. So that is the holy grail as far as the NASA is concerned. And you don't want to miss any of the high fidelity video images that are coming through. So that's the reason why we kind of reorganized how network slices could be organized. And then what we did was, this is the architecture. So this is just kind of a basic notion of how this happens. So the next 2024 moon mission, the moon base will be on the South Pole. And so you'll be able to, so from the South Pole, you'll be able to see the Earth for 15 days. And for the other 15 days, you will not be able to see the Earth. And so as a result of this, NASA has called this LunaNet, right? So this was NASA's concept that they're going to have all these orbital relays, and each orbital relay is going to have about 12 hour of orbit or time to go around the moon. So there might be different orbital planes. Each of the orbital relay will be able to support communications in different spectrum bands, right? So they are planning to have communications in the S band, the UHF band, X band, and the K band. And you might have different services. So NASA calls this like communications, which is like, it used to be called networking, but now it's called comm. The other is detection science. So what we are doing is we are adding this capability on top of the LunaNet, and that is to orchestrate these network slices. And the network slices may be a different flavor. For example, scientific data, mission statistics, which is like priority, third highest priority. Command and control has got a very high priority, and then the human life support system has got a extremely high priority, which is the EVA, or the extravehicular activity. And based on what the slice requirements are, we would be able to, configure these slices so that it can perhaps take not just one route, right? It could have multiple routes. So the same data flows from the moon base to the Earth using like different routes, because you want to provide the robustness and resiliency. So closing thoughts. Um, First of all, uh, spectrum, both spectrum sharing and network sharing is extremely important. I think that we are moving from the world of spectrum optimization to network optimization. Some of the other closing thoughts are that more research is needed on how to create these network slices over long distances, so that we can provide quality of experience that is needed. And then the other thought that I have is that the spectrum efficiency is a very outdated metric. So I mean, I really feel sad when FCC puts a stamp and says that from now on, broadband will be 25 megabits per second. Because if you don't provide 25 megabits per second, then now you don't qualify for all these grants. And that is a huge problem. Because, I mean, for people who don't have internet at all in like, really remote and rural areas, for them, even getting 10 megabits per second is a big deal. LPD links, for example, low probability detection links, the 100 kilobits per second is amazing. And for NASA robotic missions, for example, I mean, you would easily expect kilobits per second of data for EV applications, um, if you don't have 250 megabits per second links. So I think this is a very, uh, this requires a little bit of debate, because I don't think spectrum efficiency should be a metric. It should be basically like, what is the utility of a particular link? And maybe, if you don't have, like, if you only have a 6 megahertz of spectrum, you're not going to be able to provide 25 megabits per second guaranteed traffic, right? So this is very important, especially in terms of getting grants and things like that. So I think I'm going to stop here. Please let me know if you have any questions.